Hey, I'm Alvin Beyerlein. I'm from the University of Florida, and I participated in a summer research program here at the University of Michigan under the mentorship of Dr. Guy Meadows from the Department of Naval Architecture and Marine Engineering. Now, my project was the Flying Fish. It's an autonomous flight surveillance platform, which is an airplane that will stay at sea for multiple weeks at a time and monitor an area. Now, what we can see here from the airplane is that to survive at sea, we have an array of solar panels on the wings, also 3 motors which will run the plane, and a catamaran style hull, which is very important to its stability at sea. And now the key goals to this are to survive at the ocean for weeks at a time and sustain itself for the entire time. So what I have here is a quick video of the plane flying autonomously. All we did is we programmed it to hop from one space to another, and it did this all by itself. What we see here is it's constantly adjusting itself all by itself. This is one of the first airplanes of its kind to be able to do this all at sea. Now, the goals of this plane are to be able to stay at sea but endure deep sea conditions. It needs to be able to sustain itself in 2 knots of wind and waves up to 8 feet, and be able to collect and hold its own solar energy, being that there may be days where the sunlight's low or that the winds are too strong and it's going to blow itself out of its watch circle too many times. So what I did is I went to develop a method to optimize this program. And we couldn't test it in various locations worldwide, being that we don't have the resources. So we developed an environmental simulator on MATLAB. And I worked with it in that the original program was just a drift and fly function. It would stay in its watch circle. It would float all the way till it hits the edge, then just pick up and fly all the way across. And what we found when running this program was that there was a lot of energy that was unused. They would stay for hours fully charged. And we just figured we needed to develop a better use for this energy, and maybe also optimize it for different areas worldwide due to the fact that there's different weather conditions. So what I worked on was I changed 2 things. I changed its watch circle that it had to stay within to different sizes depending on the area, and I also developed a taxi routine, which is a way to use energy. What it would do was, when it was at full energy and there's a surplus of sun, it would turn against the wind and current and just taxi against it. It wouldn't fly, it would just run the motors enough that it could hold position and or go against the wind to stay within the circle for a longer period of time. Now, what I got in my data from this, as we can see here, is a few interesting things. Now, all these programs in the different areas, because we have here a key of 2 different sizes, was that the number of flights was always greatly reduced. Here, all of them, all about 20% or more. And the key thing that we were really trying to do was stay within the circle, but there wasn't really a large or significant difference. Sometimes it would be more, sometimes it would be less, and we didn't do that to our expectations. Also, a key improvement was that yes, the plane would drift out of circle, but now with the taxi program and the different areas, it would go out much less, sometimes more, but a general trend of less time outside of the circle or less distance. So, as we move on, we have a few graphs. Now, being that we have to run this plane for long periods of time, we also had to then go to the perspective of maybe a year-round deployment. And you see in different months, the plane performs very differently. In April, what we have here is, here's our watch circle, and here's its travel plans for the entire month. And you can see it drifts very far off multiple times. August does the same in multiple occasions. And January, our watch circle is all the way down here. And as you can see, it went way out. It went almost 16,000 meters. And all these different times it floats out can all correlate to these days of very low energy. What happens is it will get caught at the edge of the circle, lose its energy, and just drift out. So these are things we need to improve. Now, we'll continue on to the next slide. Now, here's our differences. Here's what I got as an improvement. So here's our original program. This program was the drift and fly function. Okay, normal, our standard radius of 2,500 meters. And what we see here is it drifted out 2 or 3 times pretty far. Now, first thing I changed was the size of the circle depending on the area. And for this area, a smaller circle was much better. As we see here, the circle is much smaller, but only drifted out once or twice, which is an improvement. Now, I also added then the taxi function. And what we see with the taxi function is compared to this, it came out much less, and it stayed within its area, closer. We have a couple small losses, but still stayed within the circle. Now, what we have here, so the overall my findings is that the taxi function does reduce the distance traveled from the center, which is great. It also reduces the number of flights taken, which could be used to help keep the plane in much better condition for a longer time when it has to work less. And what happens is it doesn't reduce the time it's spent out of the circle. So that is for our mode of improvement. Different watch circles are all very dependent on the location. As we can see back from the data before, the areas of the northern tropical areas, they required much larger watch circles, and the southern required less. And lakes, they stayed pretty constant just due to the fact there's no current and the winds are very low. Now, as we can see from my slide here, what we're really looking for is this optimal flight pattern. It doesn't leave the circle, and you can see over the course of a month, it monitors pretty much the entire area of the circle. Now, certain months we still haven't had a way to control it, as in January in the southern hemisphere we saw that it went way out and we didn't want that. So these are all for improvement. Further research would probably entail developing a better taxi routine, more robust, something to keep in the circle, and also maybe looking into changing the plane physically, add more batteries or develop stronger stronger power, stronger propellers. But overall, this would all be in future research, and thank you for looking at my project. Boom.